Hey guys, today we're going to be doing a lab, and mostly it's for the students that are in class. So students who are at home, that's who this video is for. So I'm going to show you what they're doing here in class, and then you've already been provided a data set, so you have numbers to analyze. But I want to show you what's happening so you can get the big picture of what's going on and what we're asking from you. So we have these little toys, these jumpers, and you can press them down on the table. Yeah, that's visible. You can press them down on the table, and when you let them go, they jump up in the air. Let's see if we can do a little better than that. There they go. They go up quite well. They go up out of screen. But we have attached weights to the heads of some of these, and when they weigh more, they don't jump as high. So the more that they have attached, the more it affects their height. And if they're very, very light, they go way up. And if they're very heavy, then they don't go very high at all. And we have a whole box of these things. And in class today, students will be making all of these jump and recording data to see how high they go. And the reason we're doing all this is because we want to make an estimate of how high Princess Leia will jump. And Princess Leia is a princess, so she doesn't jump for anybody. She has too much dignity. Okay, so we will excuse me. We will know how much she weighs, but we will never get to see how high she jumps. We have to make an estimate of this based on the information we get from all of the other jumpers. Okay, so figure out how high Princess Leia is going to jump. Now we also have Walter White from Breaking Bad. He definitely doesn't jump for anybody. So we also want to estimate how high he's going to go too. So in the information that you have, we've given you the Princess Leia's weight and Walter White's weight, and you have to come up with a method to estimate how high they will go. Now you will find as you analyze the data that's given that it's pretty easy to figure out how high Princess Leia can jump, and I think the reason for that will become apparent when you start analyzing the data and making a graph out of it. But Walter is more difficult. And again, you can I think you'll see why once you start crunching the numbers. So that's to show you what's going on. And now I will explain to you, try to give you some hints on how you can get a start at Walter, figuring out how high he will go. Okay, so now I'm going to show you an approach that you can take when you're trying to figure out how high Walt can jump. Okay, now the problem, and you'll probably notice this when you're crunching the numbers, is that the data will, when you graph it, won't be a straight line. It's going to make a curved line, and it's difficult to make an estimate on a curved line, especially if the point you're interested in goes off the end of the line. So for example, if you were making a graph and your graph, all your points came out to be something for a pretty straight line like this, that's pretty easy to project. You can just make the line longer and longer and longer. And then Walt, the data for Walt, this is the second complication, the data for Walt is off the end of your data set. So Princess Leia is easier because her weight is within the data set. There are some jumpers that are heavier than her, and there are some jumpers that are lighter than she is. So you can kind of figure out where she fits into the graph that you make. So you can get a pretty good estimate for her. But Walter is significantly heavier than any of the other jumpers. And that means that he is off the end of the graph someplace. Now, as I said, if they all plotted to make a nice straight line, well, that's no problem. You can just see where Walt is, make your straight line, and make your estimate of how high you would go. But you don't have that. In this case, you wind up with a curve. Now, I'm not going to tell you what kind of curve it is. I'm going to let you find that when you do your own thing. And when you're watching this, you may already know. But suppose that the curve looked, well, you know what, let's just jump to this, and I think it'll be clear from this example here. Okay, so suppose, excuse me, suppose we have this data set. So we have X values and Y values. And when X is 1/2, Y is 1/4, which would be right about here. When X is 1, Y is 1, that's about here. When X is 2, Y is 4. When X is 3, Y is 9, which is about here. And when we graph those, we get a curve like this, which you will probably recognize as a parabola. Okay, so it's a curved line. Now, if we are trying to figure out what the value for Walt is, and Walt is out here at, say, 8, okay, and this is the data set that we have, well, Walt is way out off the end. And if we're going to project this curve, we don't know how it's going to go. If it may curve a little or it may curve a lot. And the farther we get off the end, the greater the difference is. You know, if it was something like, I don't know, something like this for a curved line, and this is as far as our data went. Well, out here, I mean, does it curve like this, or does it kind of curve like this, or does it come down sharp? And if we're looking at a point way out here, well, who knows what it is? We can just get no reliable estimate by extending a curve, because we don't know if we're extending the curve right. Okay, so the way we solve this, or the way we can attack this, is we try to find some way to transform our data so that when we graph it, we can get a straight line. Because if we can make a pretty straight line out of it, straight lines are easy to extend, and then we can make a better estimate. It's not going to be perfect, but at least it's going to be better than trying to extrapolate some kind of a curve. Okay, so in this case, we could look at this curve and say, hey, this looks like a parabola. And you may remember from your math class that a parabola comes from y equals x squared, which is clearly what's going on here. 1/2 squared is 1/4, 1 squared is 1, 2 squared is 4, and so on. So what we can do is try to come up with a way to undo the curve. So what we could do is we could make another column and call it z, all right? And we're going to make z equal to the square root of y. So we're just going to take this number from our data table and we're going to transform it in such a way that we will hopefully get a straight line. So if we do this, we make z as the square root of y. The square root of 1/4 is 1/2. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3. And now we will make a plot of x versus z and see if we can get a straight line out of it. So when x is 1/2, z is 1/2. So that's going to go 1/2 and 1/2. That'll be right here. When x is 1, z is also 1. That's good. When x is 2, z is 2. And when x is 3, z is 3. And as we can see now, we're going to get a nice straight line. Let's use this. Let's see, it's going to go out this one here. Okay. Nice straight line. And even though our data set ends here, since it's a straight line, we can be more certain that our extension is going to be in the ballpark. So now we go all the way out here to 8. And Walt's value will fall right here on our straight line. And we can read across here and we get a value for z of 8. Okay, so that's very nice. So now we have to undo what we did before. So if we look at 2 in z, how do we get back to the value of 4? Well, we have to square it. We took the square root of y to get z, so if we square z, we'll get back to y. So we will square 8. 8 squared equals 64, and we would estimate that the value for Walt with the big number here would be 64 in this particular case. Now, the data that you are going to be graphing isn't a parabola like this. It's a different shape, okay? I will ask you, if you haven't already graphed it by now, pause the video and make your graph so that you can see what you're getting, okay? If you have, you'll probably agree that you get a graph. Okay, I'm going to show it now. So if you haven't paused it, Now you're back. Okay, the graph is going to look something like this. Okay, that's going to be generally the shape of what you've got. This is your x, this is your y. And this kind of makes sense because when x is small, in other words, the weight, when the mass is small, it jumps really high. So when the mass is small, the height is very high. And when the mass is large, then it doesn't jump very high and it's small. So this is sort of an inverse relationship. So what you need to do is think back to your math class and think, well, what kind of an expression, what kind of relationship here will produce a graph that looks like this? And there are a few. One of the simplest is to call this an inverse relationship. That's just a straight inverse relationship. So if you can come up with an equation which would produce something like this, then you can transform your data using some rule and see if the data that's provided when it's transformed actually turns into something that's reasonably straight. And if it's a reasonably straight line, then you can plug in a value for Walt, go up to your straight line, read your transformed value, undo what you did before to see what value you'd get for Walt. Okay, it's called linearizing data. Sometimes it comes in handy. Anyway, I hope that gets you unstuck and that you can make some progress with this. And I look forward to seeing what you come up with. All right, thanks for your time, and we will see you next time.